to our first speaker, Albert Liu from TACC, Texas Advanced Computing Center, who will be talking about Jupyter and HPC for computational chemistry. So Albert, go ahead.
Thank you, Bob. Hi, this is Albert. Today I want to talk about Jupyter plus HPC for computational chemistry. I'll give a quick overview about what Jupyter is and how to run Jupyter Notebook on TACC visualization portal. And then I will discuss how to run LAMMPS in Jupyter Notebook. In the second part of the talk, I will discuss how to run parallel LAMMPS simulations in Jupyter and how to compose workflow using a package called Parsl. Okay, what is Jupyter Notebook? The official Jupyter website describes the Jupyter Notebook as an open source web application that allows you to create and share documents that contains live code, equations, visualizations, and narrative text. So basically, Jupyter Notebook is a virtual notebook environment in which you can do, for example, basic arithmetics and define functions, do symbolic math, plot data, creative interactive interface, and so on. In Jupyter Notebook, you use code, equation, figures, tables, images, together with narrative text to tell an idea. Because using Jupyter Notebook is very intuitive, it is a perfect tool for teaching and sharing ideas. At TACC, we provide Jupyter Notebook access from our visualization portal. You can use either your TACC or Ecss account to log in the VIS portal. You can choose either Stampy2 or Wrangler to run the job. For Jupyter Notebook, you'll get one compute node for each visualization session. That means if you get Stampy2 KL node, you'll have 68 cores. If you get the Stampy2 Skylake node, you'll have total 48 cores. So after you log in, you submit the job and wait for it to start. After the job gets started, you open the Jupyter console by clicking the green Open in Browser button. Before I discuss further, I'd like to talk about what computational chemistry is about. Referring to Wikipedia's definition, computational chemistry is a branch of chemistry that uses computer simulation to assist in solving chemistry problems. Computational chemistry deals with either static or dynamic problems. The temporal and spatial scale of interest can be very different from problem to problem. Some common methods include ab initio methods, semi-empirical methods, molecular mechanics, molecular dynamics, multi-scale method, and continual approach, and so on. Some popular software includes Ember, Charms, GROMACS, LAMMPS, NAMD, VASP, Gaussian, and Quantum Espresso, and so on. In this talk, we'll mainly focus on LAMMPS. The name LAMMPS stands for Large-Scale Atomic Molecular Massively Parallel Simulator. LAMMPS is a classical molecular dynamics simulation code with a focus on materials modeling. It was designed to run efficiently on parallel computers. It was developed originally at Sandia National Lab. In general, when we do MD simulation, we first create an atomistic structure of the system you want to simulate. And then you specify the interactions among atoms. Finally, you integrate equations of motions to produce a dynamic trajectory. Then you analyze the trajectory to get the information you need. Doing MD simulation is sometimes like doing an experiment you try many different strategies and find the best one. Okay. On STEMP2, you use command module load LAMMPS to load the default version of LAMMPS. In the command line, you use LAMMPS STEMP followed by the input file to run LAMMPS. The LAMMPS module on STEMP2 was built with Python interface. So you should be able to import LAMMPS in Python and in Jupyter Notebook as well. You can either do import IPyLAMMPS or import PyLAMMPS. More information about the LAMMPS Python object can be found in the LAMMPS user manual. Okay. There are more than 200 examples included in the LAMMPS packages. In the LAMMPS package, the LAMMPS example is a good starting point for beginner. But sometimes it's hard to tell what the example is about from its name and its input file. But what if we use Jupyter Notebook to present these examples? Here I want to show you some cases. Let me switch the window. Here. Okay. Let's look at the first example, flow. So this is a Jupyter Notebook for this example that I created. So from this movie, you can see, oops. So in the flow simulation, we move the upper wall to create a coiled flow in the liquid region. This is all the simulations is about. What about another example, crack? So in this example, you can see this is the Jupyter Notebook. And we look at the movie of this simulation. You can see it simulates how crack forms in a metal slab when you apply stress to the system. Look again. Okay. So in the example deposit, this is the notebook. And you can see it simulates how molecules deposit on a metal surface. And how about next example called grain region? So in this example, it simulates the motion of particles pour into a funnel. So you have to agree that image is better than words and video is better than image, at least for presenting the result of an MD simulation. Okay, let's go back to the presentation screen. Okay. So, sorry. So in this talk, even though in this talk we mainly focus on LAMMPS, there are still many other packages that you can install and use in Jupyter. Many of those packages can be installed simply by using command pip install. The table here lists some Jupyter-friendly chemistry packages that are installed and tested on STEMP2. One of the packages in the list, GLView, is a very cool visualizer for large molecules, such as a protein. Here I want to show you some cool examples. So here is the Jupyter Notebook with GLView. You can see there are many beautiful protein images shown here. So you can use your mouse to move the molecule around. You can zoom in, zoom out. And here are some other molecules. And you can even use full screen to look at the molecule. It's pretty cool. Okay. Close this window. Okay. And there are some other chemistry packages such as VASP that cannot be used directly in Jupyter. But you can use the interface provided by ASE to use those packages. Many of the software lists here are have already been installed on STEMI2. Okay. On the VIS portal, we get one compute node to run Jupyter Notebook. It would be great if our simulation can make use of all available cores. In Jupyter, you can set packages OMP to enable LAMMPS multi-threading functions. You will speed up certain type of calculations in LAMMPS. And if you want to run LAMMPS using MPI on multiple processors, you'll need to use IPyParallel and MPI for Pi. MPI for Pi is a Python MPI binding, and IPyParallel enables parallel application to be executed in Jupyter. There are two parallel schemes in LAMMPS. The first scheme is simple domain decomposition. In the example on the left, the system is decomposed into 16 subdomains. Each subdomain is run on one CPU. So we need total 16 CPUs to run this job. In the second scheme, we have multiple replicas of the same system to simulate. In the example on the right, we have 4 replicas. Each replica is decomposed into 4 subdomains. Each subdomain is run on one CPU. So again, in this case, we need total 16 CPUs to run the simulation. Okay, in Jupyter, if you want to run a parallel LAMMPS calculation with only domain decomposition, you first need to start an IPython cluster. You can do this in the IPython cluster tab shown here. In this example, we start 4 Python engines. After that, after you start 4 Python engines, you import IPyParallel in the notebook. And then you import MPI for Pi and start LAMMPS. The magic, the cell match PX shown here means to run the command in this cell on all 4 IPy engines we just started. What if you want to what if your simulation need more than one replica of the system? In this case, we want to simulate 13 replicas, and each replica has 2 subdomains. So we start total 26 IPython engines in this example, and then we import IPyParallel in the notebook, and then we start MPI for Pi and LAMMPS. But when we start LAMMPS, we need to set the partition value here to 13 times 2 in order to create 13 replicas of the system in LAMMPS. Okay, so far we've discussed how to run LAMMPS using Jupyter Notebook on the VIS portal. We've also discussed how to turn on LAMMPS multi-threading function and how to set up the 2 different parallel schemes for LAMMPS in Jupyter. Next, I will discuss how to compose and execute workflow in Jupyter. The package I want to talk about is called Parsl. Parsl is a native Python library. It allows you to write functions that execute in parallel and tie them together with dependencies to create workflow. In Parsl, app is a piece of code that can be asynchronously executed. There are two types of app, Python app and Bash app. You can declare for the function in your workflow. Parsl creates an implicit workflow based on the passing of control or data between apps. Here are some examples of declaring Python apps and Bash apps. You can use Bash app to launch an executable. So in this example, we use it to run LAMMPS. So basically, you return LAMMPS and followed by the input file to run LAMMPS. Okay. Okay. Instead of talking about the details of using Parsl, I want to show you some examples of running LAMMPS with Parsl in Jupyter. So in the first example, it's a parallel workflow of energy minimization of iron chromium random alloy. In this example, I create 48 workers to handle 48 tasks in parallel. In each task, I first use LAMMPS to create a random alloy structure. Then I raise the temperature to melt it. And then I cool it down and do energy minimization to obtain the energy of the quench structure. So here's the notebook. Okay. So this is the notebook I want to show. So this is okay. So this movie show you the process when we melt the nanoparticle. You can see it becomes pretty messy, like a droplet. And when you quench it, it minimizes to the minimized structure. So after you run the workflow, you gather all 48 energies together because you run it in parallel. So you can plot the energies, and you can also use Jupyter to visualize all these structures of the nanoparticle you just created with the workflow. So according to this plot, the minimum energy structure is this one. Is probably, I think, this one, this particle. Okay, this is the first Parsl example. The next example, I first use LAMMPS to create the structure of two neighboring states, and then use notch elastic band method with 13 replicas to find the saddle point structure located at the energy barrier maximum. Then I compute the Hessian matrices for the initial and the saddle point structure. In this step, I use 48 workers in parallel, and each work compute just one row of the Hessian matrix at a time. And then I use the final Hessian matrices to compute the transition state theory rate prefactor. So here's the notebook I created. So this is the workflow in the Jupyter notebook. And the transition I want to look at is like this. You move this atom from this position to another position. And when you run notch elastic band calculation, you obtain the minimum energy path for this transition. And the maximum is the saddle point structure I talked about. Okay. In the third example, I use 48 workers to compute and find out the weakest CH bond in each C12 alkane isomer. There are total 355 isomers for C12, and each isomer has 26 CH bond. The procedure shown here is a little bit complicated. And here's the result of the performance test for this workflow. When I use 48 workers, the efficiency is about 50%. I get about 25 times speed up which reduced the simulation time from 96 to 4 minutes. 4 minutes of waiting time is quite acceptable when using Jupyter Notebook. You definitely don't want to wait 96 minutes to do this simulation in Jupyter Notebook. So here's the notebook. So you can see, I want to show you, okay. I can use the notebook to visualize all the isomers I create in this example. Okay, the last example I want to show is not about Parsl. In this, I want to show an interesting example for teaching, actually. In this example, we first set chromium concentration, and then we create a structure of iron chromium random alloy. And then we compute the energy of the system and plot the data. You can see I set in this notebook here. Okay, you can see in this notebook here, I can move the slider around and create different nanoparticle structure. And it will calculate the energy for this structure and accumulate the energy data and plot a summary shown here. And I believe this is a good example of showing you how to make LAMMPS interactive. And I think that's it for this talk. Thank you for your attention. I'm happy to answer any questions. Thank you.
Great. Thank you, Albert. That was fantastic. You know, I've personally been wanting to learn how to use LAMMPS for quite some time now, and could never quite wrap my head around how to get started. And this looks great. So let me just open it up. Do we have any questions for Albert?
Oh, we have a chat.
Just a great presentation. No questions?
So Bob, this is Phil. I'll ask a question. And Albert, so I was curious, I know there's different ways that the centers have made Jupyter Notebooks available through the user interface available. Do you know what's being used through the TACC visualization portal? What's running behind the scenes there to provide that nice interface and access to the compute resources through Jupyter?
I'm not very sure about the detail, but I think it's a Jupyter Hub application, right? It runs Jupyter Hub, so you can share with multiple users.
And did you say, you mentioned that each Jupyter Notebook is allocated a whole entire node? Is that is there any option to share nodes on Stampede, either through your regular queues or through the allocating through the Jupyter Hub?
What do you mean?
Can you get say one core on a node? Do you have shared scheduling of nodes on Stampede? So say you wanted to do some very light work on Jupyter on Stampede, could you get fewer, than less than the entire node?
I'm not sure you have the option to do that, at least on this portal, because every time you submit a job, it will allocate one node for you.
Okay.
But But I'm very curious. Is there a way to request 2 or more nodes for Jupyter? Maybe we can do that, but I'm not very sure on this portal.
Yeah, so Albert, this is Bob again. I'm pretty sure that Stampede 2 doesn't allow sharing of nodes.
Mm.
Okay. Yeah, I think that'll be fundamental feature of the schedulers there. And then my last question was with respect to the LAMMPS package. Do you know the details of how? So all those functions and that Python functionality comes with every installation of LAMMPS. Is that right?
Yes, but you need to compile LAMMPS as a library, and you need to enable the Python interface when you build the LAMMPS package.
And then when you load the Jupyter notebook, it's loading in terms of getting that into your importing LAMMPS into your workspace there in Jupyter. It's loading some Python installation where you've already installed LAMMPS within that Python installation. Is that right?
Yeah.
Okay.
And we have thanks, Phil. We have one question in the chat. Can this system do NAMD simulation?
I think in Jupyter Notebook you can always execute executable in the background by launching a bash a command line command.
Okay.
You can run it in the background, but you probably need to grab the output from text and analyze the data. But you probably cannot directly use NAMD in Jupyter Notebook. But I might be wrong. You can check with an NAMD developer.
Okay. Yeah. So this question came in from Hong Chung. So did that answer your questions?
But actually, like I said in the Parsl slides, you can use Parsl to launch any executable in your workflow in your system on your system. So you can use Parsl to launch NAMD, I guess.
All right, great, thank you. Do we have any more questions? All right, again, Albert, thank you. That was a fantastic presentation. I see a lot of kudos coming in on the chat, and this is something that I personally want to dive in and work with once I can carve out a little bit of time. So let me, so if you want to go ahead, unshare your screen, we will switch over to our second speaker.
Stop sharing. Thank you, Bob.
And this is going to be Alan Craig presenting on behalf of himself and Max Collins, development of a mobile augmented reality application for visualizing the protein data bank. So Alan, whenever you're ready, go ahead.
Okay, can you hear me, Bob?
Yep.
How do I get this up here? Here we go, slideshow. Hi, everyone, it's good to be here. I'll close these windows here. As Bob said, I'm Alan Craig, and I'm here to talk about a mobile augmented reality application that a student and I made for visualizing the protein data bank. Unfortunately, the plan was that Max was going to give this presentation today, but unfortunately, his grandmother passed away, and he's at the funeral right now as we speak, so he was unable to join us. He won't even be able to see this until the recording afterwards. So I think it's an interesting juxtaposition with our last speaker. He mentioned that an image was better than text and video was better than an image. This project is an experiment to see how it might be to bring that video information and data out into the real world off of the screen, so to speak, at least conceptually. Why won't this forward? There we go. So this is not an ECSS project. This was a project with the Blue Water Summer Internship program, where Max was a student in that program. And what that program is, it was located here at the University of Illinois, and Max was a participant way back in 2015, 2016. And what they did was they brought the students in for a few weeks in the summer, where they learned all sorts of things about high performance computing. And then they paired them with a mentor. And Max had expressed an interest in learning something about visualization and human-computer interaction. So they asked if I would be his mentor for this project that then was to continue beyond, once they went home from this internship. Max, just to give you some background, when he was here in 2015, he was an undergraduate student, a psychology major, and he was very interested in how technology and humans interact with each other, and interested in how much we as humans adapt to technology versus adapting the technology to the person, and those sorts of questions. I've done visualization and virtual reality and augmented reality development for quite some time. And so we talked about potential projects, and he was interested in getting something where we could try some interesting experiments with it. And that's where the project came from that I'm going to show you today. And just so we're all on the same page here, in the blurb that Bob sent out, there's a link to a story about this project, and there's a video in there, but I'll go ahead and show that video here today so that everyone has seen it. What you're actually seeing here is the screen of a mobile device. It can be either a phone or a tablet. And I'll just play this video out. And the goal, one of our goals was to say, what if we could have this data leave the page and come out into the real world with us so that we can interact with it bodily? And so here's an example of that tool in action. Again, you're seeing the screen of the mobile device, and he's typing in a code for a structure from the protein data bank, and we'll talk about that in a minute here. Oops, stop. Okay, so hopefully everyone was able to see that, and we will pick up our slideshow here. So you can see we actually created this application, and some of our goals were to allow us to see data that's housed at the Protein Data Bank. And what the Protein Data Bank is, it's a database of molecular information and structures, and there's a lot of things out there. And what we wanted to do was to say, is there a way we can more intuitively bring our bodies to bear to interact with the data that's in the Protein Data Bank? And there's different ways you can manipulate that data, and there's different ways you can represent it. So we wanted to make it such that you could interact with it in a physical three-dimensional way. And we, one of our goals was to make it available both for iOS and Android. So just to answer the question about what is augmented reality, by the way, Max made most of these slides, and so he lifted a quote from one of my books where it says augmented reality is a medium in which digital information is overlaid on the physical world that's in both spatial and temporal registration with the physical world, and that's interactive in real time. And so from my perspective, what that means is that digital information is out in the real world with us, behaving as though it's a piece of our real world, and then we can interact with it as though it's part of our real world. So why do we want to do that? Well, one, I said this is an experiment, but the physical nature of these three-dimensional structures is important. It's important to understand the spatial relationships in these things. And what augmented reality affords us the ability to bring those out as though they're physical models into the real world, and then I can bodily move around them. As you might know, if I stoop down to look at the underside of something, my body is giving me information about that. And then stand up on my tiptoes to look at it from the top, my body is giving me information about that. We can take a molecule, and we saw some great examples in the last presentation, and spin them around on our screen by using our mouse to swipe it or our finger to swipe it. And that gives us a sense of that three-dimensional nature. But what it ignores is the rest of my body's sense of proprioception. Proprioception is our sense that tells us how our body is configured, and that gives us information. So if I spin something on the screen, I can lose track of it. Am I looking at the front or the back of it? But if I either have a representation that's, and then walk to the other side of it, my body's telling me, oh, I'm on the back side of this now, and then I walk back to the front. Or if I've got it like you saw with Max with the paper there, if I twist that paper around, my arm motion is telling me, oh, I'm looking at the back of that molecule right now, and I can twist it back right to where I came from. So we can have this sense of proprioception in both augmented reality and virtual reality. The difference between AR and VR, from my perspective, really is how we treat the real world. In virtual reality systems, we isolate the participant from the real world and only present them with synthetic information from the computer. With augmented reality, we embrace the real world, bring data back out of the computer and into the real world and interact with it there. It's not that one's better than the other, they're useful for different purposes. One of the reasons we chose to go with AR is that we could make this widely available as just a mobile application without requiring any external either AR hardware or VR hardware, headsets, that sort of thing. Again, when you go into virtual reality, you put things on, you're isolated from the real world, you're isolated from your friends and colleagues, and it takes time to put it on and take it off. That's very appropriate for certain things. Our goal with this was to say, what could we do, like for scientific journal articles or textbooks, to allow something more interesting and hopefully more useful than just the photos and images that are in that document. And this can work either from paper documents or from electronic, off of the screens, you know, like off of your tablets, things like that. So our goal was to use some visualization software to look at the data that's in the Protein Data Bank and see what we could do about bringing that out into AR and then create an easy-to-use application that would be able to look at any data that's in the protein data bank using AR. So basically, we made an AR browser to the protein data bank. As we started to show this to people, some of the chemists, and especially chemistry instructors, said, well, we don't want to necessarily just have what's in the protein data bank. Sure, that's great, but we also want to use this for some meticulously curated data that people have annotated, and to maybe has annotations like arrows pointing out active regions and things like that. And so we've got that infrastructure available as well. So some of our own technical requirements, we wanted to make this run on mobile devices. That way it would be available to anyone, to high school kids, to grade school kids, without requiring external hardware. Now, we can run on devices like the HoloLens and Magic Leap, those sorts of devices, but those are expensive. No one has them. Again, you need to put them on. Those are augmented reality devices where you can see the real world, but also see the digital information overlaid in the real world. We also can push out to virtual reality devices, but that was less interesting to us. We would need to develop some additional interface to allow people to easily request data from the data bank from within virtual reality, whereas with the mobile device, we've got the ability to put that in right away. We needed real-time interaction. That was a key, because if you've ever used a mobile device, you know that speed is of the essence, and we need to have a very responsive application. So here's the nitty-gritty. We wanted to do vision-based mobile augmented reality. And what vision-based means is that we're using the camera on the device as the sensor. To create an augmented reality experience, we need to understand, the computer needs to understand the state of the real world. And so you can do that with various different kinds of sensors, and we wanted to do it with just the camera. All of these choices here we made, there were other options for. So for our development environment, we chose to use Unity 3D and C#. Now, other choices we could have done this from scratch, or we could have used some of the SDKs for some of the computer vision libraries. Unity 3D, if you're unfamiliar with it, is a game engine. It's made for creating computer games. And there's other game engines available too, such as Unreal. And we, for a variety of reasons, I don't have time to talk about all our choices that we made here, but I've developed tons of applications, and there's different libraries and different environments that are good for different purposes. So if any of you are interested in this kind of thing, I can talk about that kind of thing, why we made our choices after the fact. In order to push to the phones and the tablets, we needed to have Xcode and Android available, so we used the Xcode and Android SDKs. Those, fortunately, will communicate with Unity fairly transparently once you get it set up, so that you can, from your Unity project, push out to either Xcode or Android SDK, and then from there push out to the mobile devices. There's a variety of vision libraries available. We chose, for a variety of reasons, to use something called Vuforia. Other choices would have been things like AR Toolkit that originally came out of the U of Washington KIT lab, the Human Interface Technology lab there. There's things like LAR. There's now there is the Apple's library, which is called ARKit, and Google's, which is called AR Core. And we have a version also that uses those, and it's good for different things, but we'll always use our Vuforia one as well. For the visualization aspect, we chose to use VMD, which probably a lot of you are familiar with VMD. It's Visual Molecular Dynamics. And then the mobile app we created ourselves. And currently it's called Molecular, where the AR is capitalized at the end. You saw in the video, at that point in time, it was called VisMe. We wrote a paper, and at that point in time, it was called Vismo. And there's a variety of reasons we've changed names. but if anyone's got a great idea for a name, for a permanent name, I'd love to hear that. So we had to decide then, here was Max in this Blue Waters and Exceed Symposium, this training program of how are we going to handle all this data? This is a lot of data. And so he had access to Blue Waters. He had an allocation on there. And so what we didn't know was whether or not we would be able to visualize these molecules on demand, or whether we were going to have to do a Blue Waters run and basically visualize every permutation of every representation of every structure in there. And fortunately, as we started testing, we found that we could do this on demand. So what you saw in the video there was on demand. So as new structures are put in Protein Data Bank, they're immediately available. Can you hear me? Oh, I was just hearing a noise. Something Max was interested in was exploring different interaction modes.
Actually, Alan, hold on one second.
Yeah.
Everybody else, please mute. I'm hearing something that sounded like construction work in the background. Okay, it's good again. Go ahead, Alan.
Okay, sorry. So Max was interested in different interaction schemes, and I'll show this in a minute here. One of the core things that he was interested in is, so we've got this mobile device in our hand. Do we want to interact by using the device as an interaction device, or are we purely using the device as a lens and we interact with the digital information out in the real world? And I'll talk about that more in a second. So for any of you who have never seen, now just a little bit about how the application's created. If you've never seen something like Unity or Unreal, this is what it looks like. And here we have the game engine. And what we've got is our scene up here where we can construct a 3D scene. You can't really see it here, but down there's our target image, which I'll talk about more in a second. And then we can lay things out in 3D on that. Max took this screenshot and he configures a little different than I do. Down here, he's got a game view that shows what's actually going to show up then on the mobile device when it's running. Over here are the objects that are part of our scene. And then over here are all the parameters that go with each of these. You click on something, all the parameters show up here. Now, the important thing is that Unity and Unreal are completely scriptable. They've got an API. Every parameter in here I can control programmatically. So I can write scripts to do this. We couldn't put a molecule in here a priori because we don't know what someone's going to request. So we basically put an empty container there, and then the application makes the query to fill that in. For the augmented reality part, I hope you can see up here, Vuforia provides, back then, Vuforia was not integrated with Unity. So what we had to do that ourselves. Now, Unity comes with Vuforia already integrated. So back then, Vuforia came as a set of what are called prefabs, which is basically something you can just drag into a project. And you see here, we're using two prefabs, one called the AR camera and one called the image target. And so you drag those into your project and you can then, those allow you access to the camera, the real world camera, and it allows you to understand what's happening from the computer vision software with respect to your target image. And then see, in most AR applications, you then see objects, you know, like you might see whatever you're going to show in your scene down here as objects. But so we basically then wrote scripts that talk to the Unity API that also there's an API that lets you talk to the Vuforia prefabs within Unity. And so that's what sort of like the development environment looked like. And then you can see here, we were able to push out to both iOS and Android devices, all from a single development within Unity. And that's because we were using Vuforia, the same library for both devices. If we were using Apple's tools, you can still push from a single device if you've got both Apple's tools and Android tools on. but with Vuforia using the same library for both devices, we could then just basically push to either device as output. So I mentioned the target image. You saw in the video, Max opened up that little booklet and there was an image there. And for our current release version, we chose this image from NASA, and it's just a place, it's what it is, it's an image that can, the computer vision says, oh, I recognize that image. And the other thing it does is it's got a lot of features in this image. So what the computer vision software has to do is both say, yes, I see this image, oh, I'm supposed to put a molecule there, but it also has to determine the pose of the device with respect to the image. And so what it can do is look at the features in that image and infer, based on the distortions and what it's seeing in its camera view, where the mobile device must be with respect to that image. Now, to get those features extracted, Vuforia and the other software libraries like this provide a tool that you run outside of Unity that analyzes the image, and it builds a database of features that you can then import into Unity or Unreal or whatever tools you're using to create these things. And then the AR will magically happen, hopefully correctly. Now this is our current image. Before we had a target image, this is the one that was in the video. And you see, this is again another feature-rich image, but we also had these boxes in it because we were interested in what if we, instead of touching our phone to make requests of the user interface, we actually touched out in the real world. And so what we did was we put these boxes on here and then use computer vision. Basically, we say to the computer vision software, if this box is occluded from your camera view, it means a button press, essentially. So we turned the piece of paper into a user interaction device. We did a lot of experiments and tested with a lot of people. And the reason it's important in my mind to be looking at interacting in the world is because if you don't have a mobile device in your hand, you're using something like glasses that you're looking through, we need a way to interact with the world even though we don't have this. But I don't think people are quite ready for that. People are like, why aren't I just touching my phone or my iPad or whatever to interact? And so we give that as the option then. And here you can see Max manipulating that target. Again, with the mobile device, you can either move around the target bodily or you can move the target with respect to you. But see, he's getting a lot of information based on how he's moving that target from his arms and hands. So here's the overall architecture of what's happening. Here's our own mobile device here. From the originally, what it's doing is it's opening up the camera to see the real world, and it's providing user interface. Then the user types in their request, and what we're doing is sending an HTTP request to a server that's sitting out at Shoulder, running a web server and some CGI scripts we have, and it's also running a custom version of VMD out there. VMD is going to do the visualization for us. And so what happens then, we've got this custom version of VMD, and VMD already understands how to talk to the protein data bank. So VMD issues a request to the protein data bank to retrieve the data surrounding whatever structure was requested. So the protein data bank returns that. Then what VMD does is it takes, and we've got a protocol within our request that says, you know, what style representation we want and a bunch of different parameters that we hand to VMD. And VMD generates then the computer, the geometry and the materials for what's going to be displayed on the mobile device. So it creates a mesh and it creates the materials, and specifically it makes a .obj file and a .mtl file that then comes back to our mobile device. And then what happens is the 2D image is rendered on the device based on the perspective that the computer vision is telling the system what the pose of the device is with respect to this, and that's updated in real time as we move around. And so it appears as though that's out in the real world. It's been used on a test basis in some chemistry classes at various universities, and they've been giving us some great feedback and requests. Just to give you an idea of the current status of this, it's been ready to release for quite a while, but it will be released in a matter of days or weeks. It's been through our university's disclosure and approval process. Within the university, it has to get approval to be distributed. We had to get in place the agreement with Schroeder for hosting the VMD and our scripts out there. We had to get licensing in place with Vuforia. Oh, something about that. Back on a prior slide here where I showed you this, you can see here Vuforia watermark. That's because these screenshots were taken before we had paid for a license. Vuforia has a free development license. It used to be free to distribute, but now you have to pay a one-time fee only. Now they're changing it to a subscription, but we've got a one-time fee license for this. So the Vuforia license is in place, and we're getting ready to release that. So it'll be in both the Apple App Store and the Play Store. Since we haven't actually put it in the stores, we can still change the name. So if anyone's got ideas, we have published a paper in the Journal of Computational Science Education about this, and at that point it was called Vismo, and that's available for looking at. But if any of you are interested in testing this, I can get you a test version right now. All sorts of future plans, and I know we're about out of time here. And I think some of the most interesting things are that we do have a markerless version that uses SLAM tracking. Instead of looking at a target, what it does is it looks at the real world, and SLAM stands for simultaneous location and mapping. So it evaluates the real world, and then we can use that real world that it's evaluated in real time as though it were our image. There's reasons we still want to use the image version as well. We want to do more experiments with interaction types. We've got a bunch more apps going. We're thinking about doing a DOI-based publishing system so that any scientific journal could have enhancements in a database that all the app will have to do is look at the DOI, and it'll know what goes where in that publication. Those kinds of things. While we were waiting on legal things, we made a tool that is available. In case you're unfamiliar with it, Google now has something called Google Poly. And what that is, it's like YouTube only for 3D graphical objects. So anyone and everyone can upload 3D computer graphics. So we basically did the same thing for Google Poly as we did for the Protein Data Bank. And we've released this already for Apple only at the moment. And it's called AR Worldview, and you can get it. It's a little quirky, mostly because all these objects are coming from just anyone that wants to upload them. So consequently, they're put up at any different scale. But we have a video that shows it, and I would love to show that to you, but we're out of time. And so I guess I'll end right there. You can search on AR Worldview, and hopefully you'll be able to find the video. If not, send me an email, and I'll send you the URL to find the video that shows that off. The reason it's a little quirky is because when people make their own, they might not put the center of the world where we're expecting it, and so consequently you might have to look around for where this object shows up in the real world, or it might be so big that we're inside it, or it might be so tiny that you don't see it until you scale it up, kind of thing. So we're working on ways to kind of fix that to address that these things are all there. So I guess I'll end right there, and I'm afraid I'm 2 minutes over. I'm sorry. Any last minute questions?
Great. First of all, thank you, Alan. That was fantastic. You and Max did a great job in this project. Yes, so we are over. We started about 2 minutes late. So I think we do have time for 1 or 2 questions if we have any.
Hi, Alan. This is Mona. That was really interesting. I do have a question about multiple people viewing the same thing at the same time. Is that possible? And then also interacting, if one person does something to it, would the others be able to see at the same time?
Yeah, absolutely. Hi, Mona. Great to hear from you. That's a great question. And yes, and so that comes down more to a social question than a technical question, though there are technical issues, obviously, in supporting those. Do I want to see the same thing at the same time? So, for example, if you're looking at something, I want to see it probably from my own perspective as opposed to from your perspective, but that's a question. At the moment, we don't have the infrastructure in for me to force you to see my point of view, or to force you even to see the same thing I'm looking at, but we can easily do that. I mean, that's a pretty straightforward thing to do. So that is something Max is particularly interested in, is what does it mean to be multi-person in these kind of spaces with this kind of data?
Thank you.
Mm-hmm.
Right. Well, thank you very much. We are a few minutes over, so we should wrap up now. Slides will be posted probably within the next few days. So again, thank you everyone for participating, and to Alan and Albert for the excellent presentations.
Thanks, Bob.
Thanks, everyone. Bye-bye.
Bye.
Bye.